The nearest star to us, not counting the sun, is Proxima Centauri, and it's 4.2 light years away. Now, what does that mean? It means light traveling at the fastest speed anything can travel in the universe takes 4.2 years to get there. Light, the fastest thing we know about. Now, think about our fastest spacecraft. The Parker Solar Probe, which is incredibly fast by our standards, it's one of the fastest things we've ever built, travels at about 200 kilometers per second. That sounds fast, right? But let me put it in perspective for you. Light travels at 300,000 kilometers per second. So our fastest spacecraft is about 6/100ths of 1% the speed of light. Let me say that again, 6/100ths of 1%. At that speed, our absolute best speed right now, it would take 650,000 years to reach Proxima Centauri, 650,000 years. The human species has only existed for about 300,000 years. We're talking about a journey longer than human civilization has existed, and we haven't even gotten out of our cosmic neighborhood yet. Now you might say, well, maybe we can build faster ships in the future. And sure, maybe we can. But here's where it gets interesting. Here's where the physics really kicks in and says, wait a minute. To accelerate a spacecraft to even 10% of the speed of light, which would be a tremendous achievement, you need an enormous amount of energy. I mean, truly enormous. Let me give you a sense of it. The kinetic energy in an object is 1/2 mass times velocity squared. That squared part is important. When you increase your velocity by 10 times, the energy you need goes up by 100 times. It's not linear. It compounds. Now, if you want to carry fuel with you, which you do, because space is empty and there's nowhere to get gas, you have to accelerate that fuel too. So the fuel to accelerate is itself something you have to accelerate. This creates what's called the rocket equation, and it's not friendly. The mass ratio, the ratio of how much total stuff you have to how much payload you actually want to deliver, becomes absolutely insane. If you want to get to Proxima Centauri and back home at 10% the speed of light, do you know what your mass ratio has to be? About 10,000 to 1. That means for every kilogram of actual spacecraft and people you want to deliver, you need 10,000 kilograms of fuel and structure. Your entire spaceship would be 99% tanks and fuel. It would be an enormous vessel, mostly empty space filled with propellant. But here's the really important part, and this is what I want you to really think about. If you go to Proxima Centauri and back, if you use up all that fuel getting there, you have nothing left to slow down. You'll be traveling at 10% the speed of light when you arrive, still going full speed. You'd crash into the star at 1/4 the speed of light. That's not a mission. That's a guided missile with a very expensive payload. So you can't just accelerate. You have to accelerate enough to go there and decelerate enough to slow down when you arrive. When you put both of those together, when you calculate the energy needed for the whole trip, accelerating the fuel you'll need to decelerate, the mass ratio doesn't just double, it squares. It goes from 10,000 to 1 up to 100 million to 1. 100 million. For every kilogram of spacecraft, you need 100 million kilograms of fuel and structure. And we're only talking about 10% of light speed. If you want to go faster, say 20% of light speed to cut the travel time in half, the numbers get even worse. The energy requirements become almost incomprehensible. Now, where is this energy supposed to come from? We're not just talking about having a big tank of rocket fuel. Chemical rockets have been the best we can do for decades, and they're fundamentally limited by how much energy you can get from burning chemical bonds. It's not enough, not even close. People sometimes suggest nuclear propulsion. Now, nuclear is more efficient than chemical. You get more energy per kilogram. But we're still talking about needing civilization-scale energy supplies. We're talking about the annual energy consumption of entire countries just to accelerate one spacecraft. It's not impossible. The laws of physics don't forbid it, but it requires resources that are hard to even imagine. And that's just getting there. Let's say we actually solve the propulsion problem somehow. Let's say we have magical nuclear rockets or fusion engines or something we haven't thought of yet that gives us enough energy. There are still other problems, huge problems. First, there's the problem of what you hit along the way. Interstellar space isn't empty. It has dust, it has small particles, it has little asteroids and icy bodies. Most of them are tiny, microscopic. But when you're traveling at 10% the speed of light, a grain of sand, a tiny speck of dust, hits your spacecraft with the energy of a nuclear explosion. Literally. The physics of relativistic collisions means a grain of sand traveling at 10% light speed has the destructive force of thousands of tons of TNT. So you need shielding, incredible shielding. You'd need armor plating that's meters thick, maybe, to protect against impacts. And now you've added even more mass to your spacecraft, which means you need even more fuel, which means even bigger mass ratios. The problem compounds. Then there's cosmic rays. These are high-energy particles that are constantly streaming through space. They're coming from supernovae, from active galaxies, from violent events all over the universe. Right now, we don't have good technology to shield against them. The radiation from cosmic rays would be incredibly damaging to human beings. We're talking about mutations, cancers, damage to the nervous system. Over a journey of decades or centuries, the cumulative damage would be severe. To shield against cosmic rays, you need either massive amounts of material around the spacecraft or you need some kind of electromagnetic field. A magnetic field strong enough to protect from cosmic rays would have to be incredibly powerful and incredibly large. We've calculated what that would look like, and it would be a magnetic field millions of kilometers across. The engineering required would be beyond anything we can currently imagine. And I haven't even mentioned the problem of life support systems. A human being needs food, water, oxygen. A spacecraft would have to carry everything, decades or centuries worth of everything. It would need to recycle water, generate oxygen, grow or store food, handle waste. Any failure in these systems means death. There's no backup, no place to call for help, no way to get home. Actually, let's think about that for a moment. There's this idea of a generation ship, a spacecraft so large that multiple generations of humans could live their entire lives on it, and their descendants finally arrive at the destination. But think about what you're actually proposing when you suggest this. You're saying that we should send people on a journey that they will never return from. They'll spend their entire lives on a spacecraft. Their children will spend their entire lives on a spacecraft. Their grandchildren will spend their entire lives on a spacecraft. And maybe, if they're lucky, their great-great-great-grandchildren will arrive at a new star. Now, that raises some difficult questions about what kind of society you'd have on such a ship. You'd need strict control. You'd need to manage who reproduces, what jobs people do, how resources are allocated, and the people living there would have no say in whether they were put there. They'd be born into this situation against their will. They'd never see Earth, never experience natural sunlight, never feel rain or wind or grass. They'd spend their entire existence in a confined spacecraft moving through empty space. That's not just a physics problem, that's a profound moral problem. And then there's the problem that Robert Forward pointed out. Forward was a physicist who thought seriously about interstellar travel, and he said something very important. If you're going to send a mission somewhere, and it's going to take more than 50 years, you probably shouldn't go yet. Why? Because in 50 years, technology will have improved. A faster spacecraft will be built, and that faster spacecraft will catch up with your slow spacecraft and arrive at the destination before you do. You'll have spent a century traveling to a star, only to have a ship that left Earth decades after you arrived first. This is called the incessant obsolescence postulate, and it's a real problem for slow interstellar missions. The technology is improving so fast that it might never make sense to leave in the first place, because you'll always be better off waiting for better technology. Now, all of this assumes you're limited by the laws of physics as we currently understand them. And people sometimes say, well, maybe there's physics we don't know about. Maybe there's something out there that will let us travel faster than light or use wormholes or warp drives. And that's true. Maybe there is. Science doesn't know everything. But here's what we have to be careful about. We can't plan based on maybe. We can't say, well, someday someone might discover something that changes everything. I mean, they might. The history of physics shows that sometimes we discover surprising things. But that's not a plan. That's a hope. Right now, based on everything we understand about physics, relativity, thermodynamics, the laws of motion, interstellar travel to another star and back is practically impossible. Not theoretically impossible. The laws of physics don't forbid it, but practically impossible, meaning it would require resources and energy and technology so far beyond what we have that it might as well be impossible. But let me modify that a little bit. A one-way trip is different from a round trip. If you're willing to send people on a mission they never return from, the physics gets a little easier. You only have to accelerate once. You don't need fuel to slow down. The mass ratio goes from 100 million to 1 down to maybe 10,000 to 1. That's better, but still enormous. You're still talking about civilization-scale energy and resources. And there's another option that makes things easier, sending robots instead of people. A robot doesn't need air, water, or food. It doesn't need protection from cosmic rays in quite the same way. It can survive radiation better than biological organisms. A robot can wait. It can be dormant for centuries. A robot doesn't get bored or depressed or go insane from being in a confined space for decades. If I were designing an interstellar probe, I would send a robot. I would send an artificial intelligence, sophisticated computers, cameras, and instruments. I would not send people. And that's an important point because it changes the problem completely. Actually, you know what's interesting? Some people ask, well, if interstellar travel is so hard, why haven't we detected alien probes in our solar system? If aliens have advanced technology, shouldn't they have sent probes everywhere? And that's a really good question. It's called the Fermi paradox. Where is everybody? There are a lot of possible answers. Maybe intelligent civilizations don't last very long. Maybe they destroy themselves or lose interest in space travel. Maybe they're out there, but they're so far away we can't see them. Or maybe, and this is what I think is a pretty good possibility, maybe the physics of interstellar travel is just as hard for them as it is for us. Maybe even advanced civilizations far more advanced than us, find it's not worth the effort. The distances are too vast, the energy requirements are too huge, the time scales are too long. You see, there's something called the scale of the universe that really puts this in perspective. The nearest star is 4 light years away. That's close in cosmic terms. The Andromeda Galaxy, the nearest large galaxy to us, is 2 million light years away. That means light from Andromeda takes 2 million years to reach us. By the time light from something happening there reaches Earth, human civilizations have risen and fallen completely. We're talking about time scales that are almost incomprehensible. And in terms of energy, to move anything across those kinds of distances requires you to literally fight against the structure of space and time. You're trying to haul mass across the void at enormous speeds, and everything in physics pushes back against that. The universe, in a sense, doesn't want you to do it. Now, let me tell you something about how science fiction handles this. Science fiction writers know this is a problem, so you know what they do? They invent new physics. They invent warp drives that somehow contract space in front of you and expand it behind you. They invent faster-than-light drives. They invent wormholes that connect distant parts of space. They invent all kinds of things that let their stories work. But here's the thing about those ideas. They're not based on anything we've actually observed. They're mathematical possibilities in general relativity, sure. You can write down equations that describe wormholes or warp bubbles. But just because you can write down an equation doesn't mean it describes something real or something that's practical. For example, the Alcubierre drive. This is a theoretical solution to Einstein's equations that would allow faster-than-light travel. It's mathematically consistent. But it requires something called exotic matter with negative energy density. We've never found any such thing. We have no idea how to create it or if it's even possible to create it. And the energy requirements are absurdly large. We're talking about more energy than exists in the observable universe just to move a small spacecraft. So yes, you can write down mathematics that describes faster than light travel, but that doesn't make it real, and it certainly doesn't make it practical. I think what's important to understand is that there's a difference between what's theoretically possible and what's practically achievable. Right now, with the laws of physics as we understand them, with the technology we have or can reasonably expect to have in the foreseeable future, interstellar travel to another star is not practically achievable. It might be someday. New physics might be discovered. Technology might improve in ways we can't predict. But based on what we know right now, it's not going to happen. And you know what? I think that's okay. I think it's okay to say, this is hard. This is really, really hard. Because acknowledging the difficulty is how you actually make progress. If you pretend something is easy when it's actually hard, you waste time and resources. But if you understand the real obstacles, you can think about them seriously. So let me summarize what makes interstellar travel so difficult. First, the distances are enormous. The nearest star is 4 light years away. Light, the fastest thing there is, takes 4 years to get there. Second, to get a spacecraft there in any reasonable time frame, you need to go at a significant fraction of light speed. To accelerate to that speed requires enormous amounts of energy. Third, to get back, to actually achieve a round trip, you need to double that energy because you need to decelerate as well. And when you account for the fuel you need to carry with you, the energy requirements become insanely large. Fourth, even if you solve the propulsion problem, there are other obstacles. Impact with space debris at high speed is destructive. Cosmic rays are damaging to living things. Life support systems for years or decades of space travel are complex, and any failure is fatal. And the timescales are so long that the social and psychological challenges of living on a spacecraft for generations are severe. Finally, there's the obsolescence problem. If you wait to send a mission, technology improves. The next mission might be faster and arrive before you. so there's even a question about whether it makes sense to send slow interstellar missions at all. Now, I want to be clear about something. I'm not saying we should give up on space exploration. We should absolutely continue exploring space. We should go to the moon, we should go to Mars, we should study space, build better spacecraft, develop new propulsion technologies. That's all worthwhile and important. But we should be honest about what's realistic and what's not. Sending humans on round-trip missions to other stars in the foreseeable future is not realistic. If we ever do interstellar travel, it will most likely be one of two things. First, it will be a one-way mission, with people knowing they're never coming back. Or second, it will be robotic probes, which face much less severe challenges and don't require keeping humans alive. And you know what? Even one-way human missions or robotic missions are so difficult that they're probably not going to happen for a very long time, if ever. We have a lot to explore and understand much closer to home first. We have a whole solar system we barely understand. We've never been to Mars. We've never set foot on the moon since 1972. We haven't even fully explored our own planet. Maybe before we go to the stars, we should understand what we have here. But I do think it's worth understanding the physics. It's worth knowing why interstellar travel is so hard, because that understanding teaches you something about how the universe works. It teaches you about scale and distance and energy and the fundamental limits that nature imposes on what's possible. And I think that's valuable whether or not we ever actually go to another star. The universe is vast, and we're here on this little planet, and we look up at the stars, and we wonder what's out there. That's a natural human impulse, and it's a good one. But we should understand what the universe is actually like, not just what we wish it to be like. The universe is big. The distances are huge. The challenges are real. And that makes the actual science of it all the more interesting, because we have to think carefully about what's possible and what's not. So there you have it. Interstellar travel, at least as a practical matter, is probably a one-way trip, if it happens at all. And that's not pessimism, that's just physics. That's understanding how nature actually works. And I think that's more interesting than any science fiction because it's real.